Welcome back to your physics notes. So this is going to be over how to do free body diagrams. So free body diagrams are one of your number one tools for taking a complex situation and breaking it down into its fundamental components. Remember, forces are required to cause any change in motion. So if you have an object that is not changing motion, you should be able to look at the forces and see that they sum to a net force of 0. If you have an object that is changing motion and has an acceleration, you should be able to show the forces that cause that acceleration and how they have a net force in one direction. To start doing that, you write free body diagrams. Free body diagrams are diagrams that show the forces acting on an object in question. And I have 3 basic rules, okay? So the first thing you're going to want to do is you are going to want to identify, ID, the object that you want to look at. The object in question, okay? So you're going to draw a free body diagram for an object. You need to specifically state what object you're drawing it for. Step 2, you need to ID objects that it is interacting with. Step 3, describe each interaction in terms of a force. Okay, so let's do a couple examples. So let's say we have a monkey who is hanging from a vine. All right, so here's a monkey. There he is. He's cute. He's an orangutan. He's hanging from that vine. Okay, now you can draw your free body diagrams on the monkey, but I think it's just as easy to make a little dot. And now we imagine that that dot is the monkey. So the first thing you do is you identify the object. Very clearly, I am telling you, draw a free body diagram of the monkey. So the monkey is our object. Now identify the objects it is interacting with. It is interacting with the rope that it's holding onto. Okay? It's not interacting with the ceiling. The rope maybe, but the monkey isn't. It's interacting with the rope, and it's interacting with the earth because the earth is pulling it down. Those are the 2 objects. So you have the rope and the earth. Now, you might make things complicated and say, what if it's windy and the wind's blowing? Yes, that's true, but it's not, okay? So let's ignore the wind and just say it's a very simple problem. The only thing we can reasonably say is interacting with are the earth and the rope. So now we state those interactions in terms of a force. So we know right off the bat, the easy one is the force due to gravity is the monkey's weight, and we know that it always points towards the center of the earth. Now, the next one is also pretty easy because it's a rope, and we know that the force in a rope has to point along the rope, and we call that T for tension. Now, when you're done with this, I'm going to add a 4th rule, and I'm going to say critique magnitude and direction of net force. And what I mean by that is ask yourself, what is the monkey doing based on the description that I gave you? I said that he was hanging there and he's not moving. So if he's not moving, and a second later he's not moving, and a second later he's not moving, you can reasonably assume that the acceleration is 0, which means that the net force should be 0. And if the net force is 0, then you should see that tension and weight add up vectorially to cancel each other out. So they're both in the same dimension, the y dimension, and it looks to me like I've drawn T reasonably the same length as mg, so it's very clear that those could sum up to 0. Okay? Now, let's take another example. Let's take a box with a mass m sitting on a surface. So for this case, let's say velocity is 0, and it's staying at 0, so acceleration is 0. Okay. Again, for my free body diagram, I'm going to make a dot, and I'm going to do it on there. You identify the object, that is our box. The objects it's interacting with are the earth, which is pulling, with the earth, which, well, I'm going to give you the answers, pulling it down. But then it's also interacting with the surface of the table. And remember, there's 2 different ways that that interaction can take place, and they might both be there, or one might be there, or none might be there. There's a normal force, which prevents the box from falling through the table, and you could also have another surface interaction where that would be friction between the box and the table. So let's identify those, now describe those interactions. So the easy one is the weight. It points towards the center of the earth and has a magnitude equal to mg. We know that acceleration is 0 and velocity is 0, so there must be a force counteracting this one, and that, if you're thinking ahead, is the normal force. The table resists you pulling through. And now a very common mistake is people say, well, there must be friction because it's not a frictionless surface, and they draw an arrow either to the right or to the left to represent friction. But I want to bring you back to this. Acceleration is 0. If I draw friction pointing to the right, I would need another force pointing to the left to balance it out. And I've only identified 2 objects, the table and the earth. The earth can only pull down. The table can only either push up with a normal force perpendicular to its surface or push parallel to the surface in friction. And I can't identify that. So there is no friction in this problem. You might say, well, wait a minute, how is there no friction? Well, the surfaces are not sliding, so this is static friction. And you remember that static friction is not an equation, but it's an inequality. So this could be equal to 0. And in this case, static friction is 0. It's a very common problem they could give you where they give you a situation, they ask you, the first thing they ask is, what is static friction? If you say, oh, it's mu times n, and n is equal to weight, you would be wrong because it's 0. Okay? Now, I can have another example where now I have a block on an inclined plane, mass m. Let's call this an angle theta. And let's say again, acceleration is not 0 and velocity is not 0. So it is sliding, and I'm going to tell you, well, no, I'm not going to tell you which way it's sliding. Okay, so free body diagram. Again, draw a dot. Identify the object, that's the block. Identify the objects it's interacting with. It's going to interact with the earth. It's going to interact with the table. I don't see any ropes. I don't see anything pushing on it. The problem doesn't give me those details, so that's it. The earth and the table. The earth is an easy one. mg. The table is also pretty easy at some point because you know that it's not puncturing through the table, so there must be a normal force. And now for friction, it is sliding and it's not frictionless, so there must be some amount of friction. And the question is, which way is it going? And the answer is, you don't know, because I didn't give you that piece of information where I told you which way the block is sliding. Remember that friction tries to prevent 2 surfaces from sliding past each other. So if the box is moving up the ramp, friction would try to slow it to a stop so they're no longer sliding relative to each other. If the box is sliding down the ramp, then friction would be pointed the other direction to slow it to a stop so that they stop sliding past each other. So let's say I give you a velocity vector and I say it's moving up the ramp. Maybe I gave it an initial push. Well, now you could see friction would have to point the opposite direction. It's always parallel to the surface, whereas normal force is perpendicular, so these two should be 90 degrees from each other. And there you go. I can't think of any other objects it's interacting with other than the table, the surface, which I've used both of my options for that, normal and friction, and the weight due to the earth pulling it down. Now, remember, you critique yourself, magnitude and direction, okay? So I should see that this component that goes this way of my weight should be equal to the normal force because it's not accelerating that way or that way. But I do definitely have a net force down the ramp, which is what you'd expect. If you pushed a block up a ramp and it was sliding up, it would slow to a stop and then start sliding down. So there you go, free body diagram.